Hello, my name is Caitlin Rodriguez Rivera, and this is my Physics 2211 video lab report for Lab 1, Constant Velocity. Here is a table of contents, providing an overview of the topics that will be covered in this report. First, I would like to briefly touch upon two of Newton's fundamental laws that serve great importance within this experiment. Newton's first law touches upon how an object, in this case a tennis ball, will remain in motion in a straight line unless acted upon by an external force, an instance called constant velocity motion. Newton's second law relates the net interaction of the system to its changes in momentum, which in this scenario will be conserved since the net force acting on the system is presumed to be zero, providing us with constant velocity. Additionally, some formulas of importance within this experiment include the position update formula and the velocity update formula that work in concurrence with the initial information gathered from the system's video analysis and properties to provide a basis for the computational model constructed, demonstrating the tennis ball's predicted trajectory with respect to time. Next, I would like to discuss my video analysis created on Tracker, in which I uploaded a video of my system's movement, coordinated its axis to describe the tennis ball's motion as traveling in a positive x direction, and implementing a track on the ball's point mass to begin plotting the system's position over time, which can be visualized in the upward sloping graph to the left, obtained by the table of extracted values to the right of my video. Then, I went on to create a computational model using the starter code provided and inputting some initial information gathered from the return data of my Tracker video analysis, such as my system's mass, initial position, and observed start time, along with a calculated initial velocity obtained by taking the first and second position time sets. I also implemented some adjustments to the calculation loop that involved applying the momentum principle, or Newton's second law, in order to obtain a prediction of the new velocity, which would then be used to predict a new position at a new time interval delta t later, and looping continuously until time reached the last observed time. However, it is worth noticing that due to the assumption that the total interactions equal zero in this particular case, our change in velocity, the second term on the right side of Newton's second law, is always zero, and therefore the system's mass will play no role in the prediction. Here is a visualization of the system's predicted motion based on the code in the computational model. Next, I have a comparative graph composed of the two datasets collected from my Tracker video analysis and my predictive computational model. At earlier times, it can be seen that the model and experiment data have very little differentiation between them, which leads to the assumption that the model has a higher level of accuracy. However, these predicted positions aren't really forecasted, but are rather the result of using the initial experiment data to formulate the initial conditions for the model. Nonetheless, based on Newton's second law, we must begin with an initial velocity and position, as they are crucially important, containing the system's entire history. That is needed in order to begin making predictions of the motion future of the system. We can also see in later times that the model's position versus time plot line maintains a linear behavior, the result of a collection of predictions that could have oversighted slightly influential factors, such as the tennis ball's mass, drift, or friction, resulting in an overprediction. Now, to address some final hypothetical questions about my overall assessment, such as how my results would have possibly changed had I flipped the axis. I do not believe an interchangement of the axes would have drastically altered my result, besides a slope facing downward instead of upward, and I will maintain that the model will once again overpredict the position versus time plot line, since the computational model did not account for any possible frictional forces acting on the tennis ball, such as from the surface on which it was traveling on, which would have accounted for the ball slowing down in the experiment data. I do not believe it is possible for me to say how many forces were added together to give a zero net force in the case that I observed, since some possible forces that acted on the tennis ball were not included in the calculation of the data sets, such as the previously mentioned friction and air resistance forces, along with the constantly present Earth's gravitational force. This concludes my Lab 1 Constant Velocity video report. Thank you for watching.